The snap move calls are here that change the tile coordinates of the camera here. And then we have this update coordinates function here that gets called. And inside update coordinates VP1, that's where we should be clamping down on invalid tile coordinates. So how do we determine whether or not the TX and TY is out of bounds? And that will depend on the current tile exponent, right? Because if our camera is set to a size of 1 by 1 pixel, like a tile exponent of 0, then there's more tile positions for where the camera can be. Conversely, alternatively, I don't have mastery of the English language. Anyways, the opposite example of that would be if our camera is huge, if our camera tile size is the size of the entire world, then there's only one coordinate it can be at. It can only be at tx0, ty0. Tile coordinates 0, 0, right? If it's just, the camera is so big that it's just one tile that perfectly fits over the entire world, right? So zoomed out as much as you could possibly be, basically. So what is a valid bounds for tx and ty depends on the tile exponent. So with that said, we need to think about how many tiles wide and how many tiles high the tile map is. So I believe we have like a map width and a map height in pixels. We need to get that. And it's the data. We actually want that tile map data. So I'm gonna take Control Alt Shift F2, clear all my breakpoints, because I know this is where we want to come back to. But we need to go on a little search for that map data, and I know it's like in the global object. And so we have create tile map, and then we have a map width and a map height, right? And that tile map is the data that is off-screen, right? That off-screen tile map data that we're sampling, this is it right here. So we're going to take this, and we got to also remember that when we access this, it's inside of global data. So, you know, we could make a breakpoint here in case we want to come right back to that. And we'll just put this tx, we could actually put this at the beginning. And so this is the global data, and the map width and the map height, and these are in tiles. Oh, so that might be a little bit confusing. This is the map width and the map height in tiles or in pixels, because right, we're going to abstract those pixels into tiles. But this tile X and tile Y is the tile size of the camera, and the tile size of the camera, if it's is measured in tiles. So one, yeah, I don't know. I'm just gonna do it, and hopefully it's not too confusing. So the map width and the map height, which you could also think of as the pixel width and the pixel height of that off-screen buffer. So just a little note so that, you know, if you want to think of it differently, map width and map height is just pixel width and pixel height of that off-screen bitmap. We want to take So this is the tile span. And it's the span in pixels. So we could also call this pixel span. We could also call that pixel span if you wanted to think of it like that. Depends on how you want to abstract that out. And so how many of these cameras can you stack consecutively next to each other on the data on that tile map without any overlap, right? So what all the different cameras see is completely unique, and all of the cameras collectively cover all of the surface area of the level map. And to do that, all we need is to take the map width divided by the tile span, and then also the map height divided by the tile span, right? And that's going to give us the width in cameras and the height in cameras of the width in cameras and the height in cameras, which kind of establishes the maximum value that Tx and Ty can be. That's kind of, yeah. So what are we going to call these values? We could call it like max Tx, max Ty. We could just minus 1. I almost want to call it like width in cameras. Because we're measuring in camera tiles. Now you could call it like this, width cam and the height cam, but the problem with that is then you might think it's like the width and height of the camera, but the width and height of the camera lens is actually this tile span variable. So I feel like this width cam, height cam, that's kind of confusing. So I gotta think of a good variable name here. So I think just width in cameras makes sense to me. So let's see. Well, what do we call this? What do we call this object, right? We called it viewport 1 snapper. Okay, well, what is it snapping to? Well, it's snapping to a grid, right? And the grid is defined by, the grid cells is defined by this tile exponent, right? Which is defining the size of the camera lens in tiles, or in a tile of a certain size, right? So this says that the camera lens is 2 to the power of 6, so the camera lens is a 64 by 64 square. And what are we snapping to? Well, we're snapping to a grid. Okay, so if we're snapping to a grid, then what is this? This is the grid width in grids, right? So we could call it grid width, right? Well, what would you measure a grid in if not grid cells, right? Now, we don't really want to call it cell width because that would imply the width of an individual cell. So I think by calling it grid width and grid height, that implies, well, what are the units of the grid? Oh, cells, right? And the cells could also be thought of as tiles. Yeah, okay, yeah, I like that. So we're going to call it grid width and grid height, so GRI for grid width and grid height. And we'll make a little note here. Grid width and grid height. How big is the tile map when measured in terms of cameras stacked adjacently next to each other until they fill entire tile map 100% without any overlap. And then AKA, how big is the grid in camera tiles? So I'm gonna make that a little summary. So when I mean camera tiles, there's no camera tiles variable. Camera tiles would be, this would be camera tiles right here. So we could do summary, how big is the world in camera tiles, and just, we could just do this, camera tiles, right? So we're just saying that we can think of this variable as camera tiles, right? And then we'll make that an underscore, so when you double click that, you see that there. And we're just saying that these two, you can abstract when you're thinking about what's going on in your head. You can abstract it as either camera tiles or tile span, depending on how you want to think about it. So grid width and the grid height. Okay, so we got the map width, map height, and the tile span. Okay, so we got what we need for the grid width and grid height, and then all we got to do is cap the values, right? So if underscore.tx is the let's do the easy one first, right? So if it's less than 0, then we just set the tx to 0, right? And then same thing with y. Let's do the easy one first. If it's less than 0, then ty, we're just going to make that 0. So cap, so lower bounds, right? Lower bound. And then we can take these guys like that. Okay, and now we need to do a similar thing with the upper bound. So, which is the harder case, right? Because it's going to be, remember, we're going to remove those off by 1 errors. So if it's a 1 by 1, if the camera is so large that it fits the whole world, then you could only be at tile 0, 0. But the grid width would be 1 tile. So we definitely need to subtract 1. Or, well, it depends on how you want to do it, but I'm going to do it like this to say that if we're greater than the maximum index that it could be, it's greater than grid width minus 1. You know what? Screw it. I'm going to do var max tx like that. That looks a little bit weird, but let's just do it. Grid width minus 1. So here's the maximum tx value, and then the maximum ty value. So this is an inclusive maximum, right? Because we're going to include, it can be less than or equal to these, right? So the grid width and the grid height. Grid width, grid height. Okay, and then what we do is we do, you know what, well, okay, mx, we could just use mx and my. Usually we use that to mean mouse x and mouse y, but in this context, I think it'd be okay. Just keep that a little bit more terse. Just make a little note that it's the maximum tx and the maximum ty, and then we can break that apart like that. And also we could do it like this, max index. And then we could do this, mx for the maximum x and the maximum y. mx, my. So that just makes it so everything can line up a little bit easier and we're not using up too much space. And then mx. So if it's greater than mx, then we want to put it back at the last valid index, which is mx, right? Because it's the max index, and this is inclusive. Inclusive. Okay, that goes off the... you're just going to have to remember that it's inclusive, because I don't want to use up all that space. Okay, so tx, and then we want to do the same for y's. So my, mx, tx, ty, mx, my, tx. Okay, so that all looks about correct. And so I'm looking at this comment here. When measured a summary, how big? Okay, so that is this right here. I just want to make sure that it's obvious what this big long comment chunk is applying to. And then, okay, so let's give this a run. So what I'm expecting is kind of like similar results, but I don't want to see any of that white because I'm not going out of bounds anymore. So if we refresh, okay, so that's what we expect initially until we press the arrow keys, right? Because right now the viewport, what do we call it? Snapper something or other. The viewport 1 snapper is not modified viewport 1 at all yet because I have not pressed any arrow keys. Oh, wait, you don't even see what's going on here. So this is what we get initially, right? Because we haven't pressed any arrow keys, right? So viewport 1 has not been adjusted by the viewport 1 snapper. But now when we press the arrow key, arrow up, okay, so now we get some color. So we're going to go down. Okay, there. Okay, we found a diagonal line. And now if we go right, up, right, up, right, up, right, up. Oh, hey, I lost my line. Right, up. I'm going to guess that, yeah, we're at the upper corner, maybe? Oh, you know what? I'm going to guess that the, okay, well, we're at the top edge here. Okay, so now we're all the way at the top right, because when I press up and right, I'm just there. So if that's correct, then, well, I'm not sure if this line, I'm pretty sure this line is in the midline, so let's go like this. So now we're going down and to the left, and if we keep on doing this, we should eventually get to, yep, to the other side. Very cool. So if we go up like this, so now what we effectively have is a camera that is kind of like moving around the world, right? Because we're gonna assume that all these pixels are eventually going to be tiles, right? Right now we're just rendering the pixels as pixels, right? They're just pixels that we've zoomed into a bit, but eventually we're going to render them as tiles. But first we want to get some of the basic, logic working first. So one more thing before we close up shop here. Let's change some sizes here. So the tile exponent. Well, I know I have a 512 by 512 tile map in that buffer that VP1 is looking at. So if I use 512 by 512, I should get like this camera that just can't move because it's zoomed out so much. So with that, let me just count on my fingers again. So count the exponents. So we're going to start at 0, right? And 2 to the power of 0, right, is going to be 1. So 1, 2, 4, 8, 16, 32, 64, 128, and 256. So it should be, counting on my fingers, I got a 9 here, but we got to subtract 1 because we started counting from 0. So 2 to the power of 8 should give us 512. So let's look at our, I'm gonna grab a calculator. So 2 to the power of 8. And so let me show you. So I got Google open. So 2 to the power 8, no, that's wrong. That's 256. So where did I screw up? I don't know, but we obviously know that the next power of 2 is going to be 512. So we need that camera exponent, the tile exponent, to be 9 to get a 512 by 512 camera, or 512 by 512 viewport, whatever you want to call it. And so we're going to do that, but first I got to stop recording because my timer just went off, and then I'm going to record another video.